Welcome to the satellite communication course. Today we start here with a high power amplifier that are required in a satellite communication. That high power amplifier, once your signal is up converted, then signal is to be transmitted from the earth station to the satellite. Once your signal is down converted, then that signal is to be transmitted from the satellite to the earth there. Now when we transmit a signal, so for the earth station, we require a EIRP, that is effective isotropic radiated power, and that is the requirement of EIRP of the earth station that will transmit the signal to the satellite. So now that EIRP, if we consider that EIRP, it is nothing but a transmitted power and the gain of an antenna there. So now to increase the transmitted power, so we require a high power amplifier here so that your power will be amplified. So now if we consider the EIRP for the earth station, that EIRP for the earth station is to be higher than the EIRP of a satellite there, because we are transmitting the signal from the earth station to the satellite. So in that case, whichever the uplink power is there that is transmitted from the earth station, so there does not have any limit on the carrier to noise ratio at the receiver. So combined carrier to noise ratio is nothing but what, AC by N, that is for the transmitter, and AC by N, that will be for the receiver. So we'll get that a combined carrier to noise ratio. So to achieve that high carrier to noise ratio, so we need to use a high power amplifier so that we'll get that a desired value of that EIRP. So again we can consider that along with this high power amplifier, that gain of an antenna is to be high if the large gain antennas are used, so then EIRP will be improved here. So we can consider that a large gain antenna so that EIRP will be higher. Means we have a scope to improve the EIRP with the transmitted power as well as the large gain antenna. But in the case of a large earth station, so that large earth station, they are a input from the various channels, and that input from the various channels are combined using a terrestrial interface model, and then that will be transmitted to the satellite. So in that case we require the EIRP is large, because for the transmitter, for the large earth station, if you see that, so input is from the various component. Input from what? From the television channel, then we can say that from the telephone channel, then input is from the, we can say that, a data, that is a computer data, or we can say that a audio or a video. So likewise a various input is there. for the largest. So for the larger station, the input is large. Okay, there is more combination of the input. So that's why the EIRP required for the large earth station is a large. But if you consider that a small earth station, in small earth station, what happened? That requirement is a small here. Means that small earth station handle a small data. So they handle a small data and large earth station handles the large data here. So that is about in a small earth station, they handle a small amount of a data. So that's why we require a power to be transmitted from the small earth station, that will be in terms of a few watts, because it has only a one channel. Either it has a voice channel or it has a data channel, and that is to be transmitted. So small earth station, nothing but we can say VSAT. It has only a small data, only one channel is there, that is to be transmitted data to the satellite. So that's why small data, so it is to be transmitted. In that case, EIRP will be small there. So small EIRP means what? The output, power output of this earth station, that will be in a few watt, and that can be transmitted to the satellite. So based on this earth station, whether it is a small earth station, large earth station, or a medium earth station, that are depending upon that what type of a data is transmitted through this earth station. And again, that larger and smaller station is are again depending upon that size of an antenna. So that earth station that will transmit a large amount of a data or a small amount of a data. So that's why the power requirement will be large or small according to the size of an earth station there, or size of an data there. So that's why we require a high power is to be transmitted from this power amplifier. So if we have a larger station, so power amplifier requirement for the larger station is high. So it will transmit a power in terms of a kilowatt, or we can say that in terms of megawatt. Okay, likewise. But if you consider the small earth station, it is transmitting the power in terms of a few watts there. It is in a for large kilowatt. So that's why the power amplifier that are used for a earth station is different according to that requirement of a data there. So generally in a earth station, they have the various power amplifier used, that is called as a traveling wave tube amplifier, that is we say it is a TWTA. Then we can say that a Klystron tube amplifier. Then we have a solid state power amplifier. Then we can say that a cross field electron tube amplifier. In the most of the applications, these three are used. That is traveling wave tube amplifier, Klystron tube amplifier, and a solid state power amplifier. So if you consider that all these three, so that generate a large power. Suppose if you consider that a first one, a traveling wave tube amplifier. So that traveling wave tube amplifier, it generates a high power. That power in terms of what? A kilowatt there, and it has a, we can say that it has a wide bandwidth there. Means we can say that it will operate in the wide band there. So that's why traveling tube amplifier is called as a wide band amplifier. So now if you see that a construction of a traveling wave tube amplifier, so it has a slow wave structure inside it, and through that slow wave structure, your signal is propagating through the slow wave structure. Now we can see that that slow wave structure can be helical, can be zigzag, or anything else. Okay, this one is nothing but a tube, and through this tube, the signal is supposed to be propagating through this tube. Okay, right now it's overlapping. Okay, this is about a RF input. Will get that a RF output, and here magnetic focusing is used to focus the electron. It is to be propagating through this particular tube. Here we can say that, and at the end, here is a collector, and here we can say that it has a cathode heater. So it emits the electron, and that electron to be propagating through this helical structure. This one is about your electrons are propagating through this helical structure. So means it has only a tube. A tube is likewise. Just if you see that a tube is likewise. So I, okay. So this is about a simple tube, and your electrons are propagating through this tube. So here we have a focusing magnet to be used, and that focusing magnet, this is nothing but a helical structure. This all these are nothing but a focusing magnet that will focus the electrons to be propagating in the given direction. So that if you see the TWTA here, so it has a tube here. Okay, if you consider that it is about a helical tube, and here we have the cathode, and here we have the collector. Means we can say that your electrons are collected at this particular place. Means this is nothing but a anode. So this one is about a cathode here. So now through this helix, electrons emitted from this cathode that will be traveling through this helix there. Okay, means what we can say that if we are heating this cathode element, so electrons are propagating through this, so that will be propagating through the helical tube. Now this helix is nothing but a spring. Now we supposed to be consider that this one is about a spring, and through that spring your electrons are propagating. Suppose that spring is nothing but a tube you consider. So electrons are propagating through that particular tube, and then that electrons will be collected at this collector there. Now these are the magnets around this particular tube we are using in this TWTA, and that magnets are used here to focus the electrons, that is that electrons to be focused, that electron is to be propagating through this helix only. Suppose electron emit from the cathode, suppose it can be go anywhere. So mostly we can say that in general case, if that electron emit from the cathode, so it start moving. So some of the electrons may go any direction. So in that case, to avoid that any direction, so we can use a focusing magnet. So that's why that focusing magnet that are used here focus the electron into a beam that will be going through this helical tube here. Now, the principle of amplification in that TWTA is that when we apply the RF input, RF signal to this helix, then what happens? From the same time that electrons are emitted from this particular cathode, then means we have the RF input from this end, electrons are emitting from this here. Then what happens that electron impart their energy to the RF field, and because of that energy, that RF signal is get amplified there. Now, if you see that, so amplification of this at each and every helix, if you see that your signal get amplified from at each and every end. So this is about a smaller signal, so it will be amplified likewise. So it will be amplified like at this point. So amplification will be takes place at each and every level, so that we'll get that a signal amplified through this helix. Means your signal get amplified at each and every helix structure because electron provide their energy to this RF signal, and then because of that your RF signal get amplified, and then once that electron give up the energy to this RF field, so that electron velocity will be slow, and then that electrons will be slow, and that will be propagating through this helix, and then that will be collected at this anode here. Now that electron beam are generating from this cathode, that will tell you, or that will gives us the what will be the amplitude here. So means we can control the electrons emitted from this cathode, so that we can control the amplification of this RF signal there. Because that energy of the electron beam that will be transferred to the RF signal, because your RF signal is propagating through this helix. So electron provide their energy to this RF signal, so that RF signal get amplified while it traveling through this tube here. So that's why we'll get that output will be amplified. So this is about a function of this traveling wave tube amplifier. Again, if you see that some books might have used a tube in a different way. Here is the alternator is there, because it's supposed to be any reverse signal come from this RF output. So again, it will not be amplified. So that's why somewhere, if you see that alternators are used, means reverse signal will not be amplified. Only signal will be amplified. So that is about a TWTA, or a traveling wave tube amplifier there. So that traveling wave tube amplifier that will be used in a earth station for transmitting the signal. So you can say that for a transmitting the signal, we can say that is about a uplink frequency signal, and that uplink frequency signal is about what we can say that supposed to be, if it is a 6 gigahertz of a uplink signal frequency, then operating bandwidth is about a 500 megahertz. So that's why we can say that it has a wide band of a operation there. So means we can say that a 10% of a approximately a 10% of the carrier. It is approximate, if it is 10%, that's 600 megahertz. So generally this provides you the wide band of a operation. So that's why the traveling wave tubular amplifier are used in the earth station for uplink, or transmitting the signal from the earth station to the satellite there. Another amplifier is a Klystron tube amplifier. That Klystron tube amplifier, it has a higher efficiency. We can say that it has a higher efficiency and a high gain. And the bandwidth as compared to the TWTA, it is a very small. It is not used for the wideband operation. It has a small bandwidth there. And Klystron tube amplifier, it is to be used in a small earth station, or we supposed to be consider that this type of, because of a small bandwidth, that will be useful for the transponder there. Because a transponder typically, if you consider that a C band transponder, suppose. So for a C band transponder, it has a bandwidth of a 36 megahertz, or if you consider that a KU band of a transponder, it has a bandwidth of a 72 megahertz because of a small bandwidth. If you consider that a TWTA, it has a 500 megahertz of a bandwidth. So that's why this Klystron tube amplifier, that is to be used for the specific band of a operation there. Now the principle, if you see that in the Klystron tube, the name itself, it is saying that it has a tube. So that tubes are nothing but it is called as a cavity. So if you see that a Klystron tube has a two glass tubes, and that two glass tubes are nothing but a two cavities. So one cavity is called as a catcher cavity, and another cavity is called as a puncture cavity. So this is about a Klystron tube here. I'm just going to draw here. Okay, maybe I supposed to hope that you people are able to understand that what I am saying, because this one a cavity, so that is called as a puncture cavity. This one is about a catcher cavity, and then we will get that output from this. We can provide the input to this. So this is about a RF input. We'll get that the RF output here. So this is about a electrons emit from this. This one is about electrons, and here it is called as a collector. So now electrons are emitting from this. Likewise, when electrons will reach to this buncher cavity, so that particular a cavity, it has some a gap voltage, or we can say that that gap voltage because of this RF input circuit. Okay, whatever the RF circuit. So means that gap is nothing but what we can say that a likewise. So this is about your RF input. That is about a sinusoidal in nature. So suppose I am going to draw this likewise. This one is about a RF here. So according to that, we supposed to be see that this one is about a cathode. Now it emits the electron. What happened? Those electrons emitting with the positive half cycle, they will be accelerated. Those electrons moving through this negative half cycle, they will be decelerated, and those electrons moving with the zero change in the RF field, so they are having the constant velocity. Means here the acceleration, or we can say that velocity, it will be a faster here. This will be a slower here, and then at that specific place, they forms the bunch. So here the buncher formation takes place. This is about a applicate diagram. Means we have the electrons from this tube cathode here. It emits, those electron emits with a positive half cycle, so they will be accelerated. Means they will move faster. The electrons move from this negative half cycle of RF input. They will be decelerated, so it will be slower there. And the electrons moving at the transition of a zero variation in the RF field, so that electrons moving with a constant speed. Okay, that speed of that electron will be a constant. Means what happened here, because of that acceleration and deceleration of electron takes place across this buncher cavity. This is about a buncher cavity. So if you see that we have the cathode, that cathode emit the electron. Okay, because we say that cathode gun or cathode get heated, then it will propagating or it will generate the electron there, and then electron beam that will be propagating through this, and then that beam will be captured at this particular place, that is at a collector, that is nothing but a anode here. Now those electrons are propagating through this buncher cavity. Yes, we have the electrons here that is propagating through this cathode to the buncher cavity. So before that we have this focusing magnet as well as the accelerating anodes. So means that accelerating anodes require because to focus the electron in the given direction. Okay, so the electrons whichever come from this particular place. Okay, so if those are accelerating here, so that will be collected at the anode, and we have the focusing magnets. They will focus the electron in the given direction. So magnetic focusing required here, so that electrons will move through this eccentric. Now because of this application of this RF field, when the electrons are moving through this, so electron has some velocity. Now that electron has some velocity, because of that electrons are moving at a positive half cycle, then they will increase their speed, and those who are propagating through this negative half cycle, their speed is going to be reduced there. And because of that accelerating of electrons and decelerating of electron, means velocity of that electrons will be changes, and that is called as a velocity modulation. And because of that velocity modulation here, so at some particular place, that electrons will form the bunches. So they will form the bunches, and these bunches are propagating through this cavity gap. And those bunches, they will be collected, and then they will be collected at the collector here. Now in that particular bunches, so electrons are form the bunches because of that accelerating and decelerating at some particular place. They form the bunches because the electrons, more number of electrons will reach at that particular point. So that bunches are formed because of that density modulation. Then that bunches are moved forward toward this another cavity. Then there is another cavity. That another cavity, we can say that is about a catcher cavity. When that bunches came near to this catcher cavity, then that bunches give up their energy to this catcher cavity. So because of that giving the energy by this particular bunches to this catcher cavity, so RF field will get amplified here. So that's why that there is a strong field in this catcher cavity, and because of that strong field in that cavity, so RF will get amplified here. So that's why we'll get that a amplified output from this a catcher cavity there. So now this particular Klystron tube amplifier will work based on this buncher cavity as well as the catcher cavity, and is about the distance between this place to this place. It is called as a drift space. So in this region that electrons are moving, and that distance between these two cavity can be adjusted so that we'll get that a highest output. So this one is a two cavity or two tubes Klystron amplifier. So if you wanted to increase the again a power, so we can use the multi cavity Klystron. So instead of a two cavity, we can use a multiple cavity. But input cavity will be a buncher cavity, and output cavity is to be a catcher. So in between that, you can add a more number of cavities so that your output will be increased. Okay, so that's why this a Klystron tube amplifier that can be used in this satellite communication there for the given particular band, and it has a typical output is about a 3 kilowatt if it is to be work in a C band, and if we consider that a Q band, it has a 2 kilowatt of a output here. So that is about a Klystron tube amplifier. So now if you consider this traveling wave tube amplifier and a Klystron, okay, if this two amplifier, if you consider that, so now this will generate a large power. So that's why for the large earth station or a medium earth station, these Klystron tube amplifiers are used. But nowadays, if you see that a small earth station, for a small earth station, a solid state power amplifier is used. That is SSPA. So this solid state power amplifier, it has a low power handling capability, or it will generate, or it will work for this low power application. It generates a only low power. But if we consider that a traveling wave tube amplifier and that Klystron tube amplifier, so now these tubes get heated, so we require a coolant here, as well as this will get heated. Okay, this TWT is again get heated. So that's why in terms of the reliability, if we consider here, the solid state power amplifier is highly reliable as compared to the TWTA, or we can say that a Klystron tube amplifier. Okay, we can say that Klystron tube amplifier. So that's why in the most of the cases, a reliability is large in this particular solid state power amplifier. Now this solid state power amplifier, they are designed using a gallium arsenide field effect transistor, GAASF it is here, and that provides a power output of a 50 watt if it is operating in a KU band, or if it is operating in a C band, so it will provide the power of a 30 to 45 watt if it is operating in the C band. But if you consider that a solid state power amplifier, because of the high reliability, and if we require to generate a large power, then we can use a parallel combination of a solid state power amplifier, so that we'll get that a large power output. Which in general we can say that a high power amplifier, it is supposed to be operating at a 500 watt or a kilowatt there. So to generate that particular high power amplifier output or power output up to 500 watt or a kilowatt, so in that case we can use a SSPA with parallel combination or a series combination, so that we'll get that a large output. So generally requirement for the C band and K band, suppose if you consider that it is about a 30 to 45 watt and it is generating a low output there, so in that case we can use a solid state power amplifier to generate the large power. So now how we can use here? Then we can consider the combination here. So whatever the input we are providing, so power input, then that power input is to be applied to the power divider, will divide the power. Then because a input required for this solid state power amplifier is small, so that's why we can consider that we have the SSP here. Then again we supposed to be consider power divider. Then again we have the SSPA because it is dividing the power. That's why we can say that we have the SSPA here. Okay, these are the power SSPA here. Then output, because we'll get that a amplified output. So then this amplified output, that is to be given to the a power combiner. So this one we can consider that a power combiner. Then again output of this power combiner, again it is to be given to the power combiner, and then we'll get that a power output here. So we'll get that a large power output. Now input power, we'll divide that input power. So then power will be divided here, and then that power divided, that will be again applied to the, here we have a solid state power amplifier. Then again it will be divided, then again it will apply to the solid state power amplifier. Then it will be combined. Okay, both it will be combined. Then again it will be combined by this both, and then it will be applied. So that will get that a high output power. So this one means that we are dividing and we are combining the power. So the output of this combiner here, again it will be combined, we say. So because of that, combining the power, so we'll get the large output power there. So this way we can use a solid state power amplifier, because we are not going in detail about that how that gallium arsenide FET is used, how it is work. Just say that this solid state power amplifier, that is to be used for the amplification purpose. So there are the various solid state power amplifier. So that can be useful for the different band. That band will, it can be of L band, S band, C band, X band, or a QU band there. So we can use A GAN-SPA, that is about a gallium arsenide device, or we can say that we have used here a gallium arsenide. Instead of that, we can use, so earlier we can say that we have the gallium arsenide fate here. So instead of that gallium arsenide fate SSPA we have. So instead of that we can use a gallium nitride SSPA. And this gallium nitride SSPA, it has a high electron mobility. So because of this high electron mobility there, so it has a more advantages as compared to this gallium. So that's why this can be used for the various band of a operation there. So similarly, we can use the SSPA by combining and dividing power amplifier. So similarly, we can use a gallium nitrate amplifier in a parallel so that we can generate a large output power there. That is about we can say that a SSPA, and the efficiency for this gallium arsenide SSPA or gallium nitrate SSPA, it is depending upon which band of operation is there. Suppose if we consider that it is to be useful for this C band there, so in that case approximately we are getting the efficiency of a 50% there. So that is about a gallium arsenide, or we can say that a solid state power amplifier. Then another example of this that power amplifier, we say it is about a cross field amplifier. So now that if we consider that a cross field amplifier, so we have that electron beam focusing, and we have the magnetic field is there. So if you consider that it has a anode, and sorry, this one is cathode and this has a anode. So that anode structure is likewise. So that's why we can focus that electron. So this is about a cross field tube like structure. So because electrons emit from this, it will be collide here, and then we'll get that amplified output there. So means we can say that here electron field and magnetic field are perpendicular to each other. So that's why a cross field amplifier. So cross field amplifier means what? E and H both are perpendicular here, and that is mechanism is used in a cross field tube amplifier. That will be what? A forward cross field amplifier or backward cross field amplifier. But this amplifier has a low gain, low bandwidth. So that's why for this low bandwidth and a low gain, but that size of this particular device is small, and it has a high efficiency as compared to the TWTA and Klystron. It is a low weight. So that's why this can be used for the space application there. That is about a crossfield amplifier. So not go in detail. So then we supposed to be consider that again a low noise amplifier. That low noise amplifier that are used at a receiver there. So generally we need to be consider that a low noise amplifier, that is a gallium arsenide fate, that is used in a low noise amplifier. So this low noise amplifier, it is used at a receiver there, and that at a receiver, so that noise temperature will decide the overall performance of the amplifier here. So generally we can consider that a low noise amplifier, its gain is depending upon the noise temperature, because this will to be useful for the a downlink, or this will use at a receiver there. So that's why that a low noise amplifier, it is depending upon that what will be the size of an antenna. So means that a noise figure of the low noise amplifier, it is totally depending upon that what will be the a noise figure. Again, it is depending upon what will be the noise temperature there. So if you reduce that a noise temperature and the size of that antenna, so then we can consider that, or we can improve the performance of a low noise amplifier. So that's why if that noise figure is a low, then we can say that that low noise amplifier, the output is a high. So now it is, and again we can consider that size of an antenna is to be small there. So there are the various low noise amplifier that are used in the receiving station or in the satellite. So that is about a amplifier. So even if we can say that a parametric amplifier again that are used in the earth station or in a satellite. That's all about your high power amplifier and low noise amplifier. So in next session we'll see that what are the components used in the earth station, that will be for the up converter and a down converter.